myself Prayak Patel, working as assistant professor in IT/ICT department in LJ Institute of Engineering and Technology. Now in today's video lecture, I will discuss about the one new concept of the graph theory. It is Hamilton path and Hamilton cycle. Now how we can find the Hamilton path or how we can find the Hamilton cycle from the graph. Now for understanding this purpose, first we understand what is path and what is cycle. So we already know what is path. Now revise the concept of the path here. If no vertex of xy walk occurs more than once, then the walk is called the xy path. Now in walk we can say that we can walk like this, no any node or no any edges is repeated, then we can say that it is a path. So it is a trail in which neither vertex nor edges are repeated. So no any node and no any edges is repeated in this path. As path is also considered as a trail, so we can say that path is an open walk, not as a closed walk. We can consider the closed walk, then it is not a path, it is a cycle. So now what is the difference between path and Hamilton path? Now in path we not consider each and every node, but in Hamilton path we have to compulsorily cover all the nodes. So here this is considered as a simple concept of path. Now here one path is available like 6 to 8, 8 to 3, 3 to 1, 1 to 2 and 2 to 4. So here we not cover the node 5, 7 and 9. So this is considered as a path, not considered as a Hamilton path. Now what is the cycle? Cycle means it is considered as a path, but starting point and ending point are same, then it is considered as a cycle. So traversing a graph such that we do not repeat a vertex nor we repeat an edge, but the starting and ending vertex must be same, then we can say that this is a cycle. So here one cycle is available. So example of this cycle is like 1 to 2, 2 to 4, 4 to 3 and 3 to 1. Green shaded line is considered as a covered edges and green shaded node considered as a covered node. So in this graph 6, 8, 7, 5 and 9, these 5 nodes is not covered. So this considered as a cycle only, not considered as a Hamilton cycle, because in Hamilton cycle we have to compulsorily cover each and every nodes. Now consider the next concept as a what is the definition of Hamilton path. Now if G equal to VE is a graph or multigraph with mode V greater or equal to 3, a Hamilton path is a path and not a cycle in G that contain each vertex. So here compulsorily you have to contain each vertex. Now meaning of the path is no any node and no any vertex edges is repeated. And here Hamiltonian concept is cover each and every node. That means we can say that cover each and every nodes without repetition of any node and without repetition of any edges. So it is considered as a Hamilton path. Now here one Hamilton path is available in this figure is like first visit node A, then A to B, B to C, C to D and D to E. So here this is a path because your starting point is A and ending point is E. Now in path we cover each and every node A, B, C, D, E. That means this path is considered as a Hamilton path because we cover each and every node and no any node and no any edge is repeated. So we can say that this is a Hamilton path. Now we already know the one concept as a Euler's trail and Euler's circuit. So here what is the meaning of Euler's trail? In Euler's trail consider the concept or condition is cover each and every edges. But in Hamilton path we have a condition is cover each and every vertex. So remember this point. Now for the second graph, find the Hamilton path for this graph. Hamilton path is possible in this graph means cover A, B, C, D, E all the nodes and without repetition of any node. So here path is possible like starting point is E, then A, then B, then C and D. So this is a one Hamilton path for this graph. Now in any graph more than one Hamilton path is possible, So this is a one example how we can find the Hamilton path. Now consider the second figure. In second figure, Hamilton path is possible or not. Now check. So here we start the process from node F, then F to A to D, D to C, then C to we have a two possibility, B or E. If we visit B, then E never visited. If we visit E, then B never visited, because after visiting B, for covering the node E, we have to compulsorily move from B to C and C to E. So node C is repeated. Now no any node or no any edges is repeated in allow in Hamilton path. So we can say that no any Hamilton path is possible in this figure, because here for covering each and every node we repeat the sum node or we repeat the sum edges. So it is not possible in Hamilton path. So this figure not containing Hamilton path. So we can say that this graph is not containing Hamilton path. Now next definition is Hamilton cycle. Now we already know what is the cycle. Cycle means cycle no containing more than or repetition of node is not allowed. Repetition of edges is not allowed in cycle. Now Hamilton cycle means your starting point and ending point is also same. We already know what is the cycle in previous slide, but in cycle, in simple cycle we can say that you are not need to cover all the nodes, but in Hamilton cycle you compulsorily cover each and every nodes. So we can say that each and every nodes cover exactly once, not more than that or not 0 time also. So cover each and every node, no any node and no any vertex, or we can say that no any edge is repeated. If G equal to VE is a graph or multigraph with mode V greater or equal to 3, we say that G has a Hamilton cycle if there is a cycle in G that contain every vertex in V. So we cover each and every vertex in V, and your starting point and ending point must be same because it is a cycle. So this figure is considered as a Hamilton cycle. We visit one by one each and every node. No any node is repeated, no any edge is also repeated. In second figure also we consider the graph as a Hamilton graph because here one Hamilton circuit is available. So most important concept in Hamilton path or Hamilton cycle is, if given graph is a Hamilton cycle is available, then we can say that this graph is a Hamilton graph. So remember the definition of Hamilton graph is like, if the graph having Hamilton cycle, then we can say that this graph is a Hamilton graph. Now if in a graph Hamilton cycle is available, then we can say that in this graph Hamilton path is available, but reverse is not possible, or we can say reverse is not always true. Now consider the another example for the Hamilton cycle. Now in this graph Hamilton cycle is possible, yes. Consider the one cycle as a first visit the node A, then B, then C, then E, then D, and then A. Now in this way we visit the each and every edges. No need to visit each and every edges, but we have to visit each and every node. So here we visit all the nodes. Now no any node and no any edges repetition is allowed. So here no any edge is repeated. Here vertex is repeated, that is only starting vertex. So it is allowed because in cycle one starting and ending vertex is same. So this repetition is allowed. Now in second figure, here Hamilton cycle is possible or not. Now we already know this graph not containing the Hamilton path. So they never containing the Hamilton cycle. So we can say that this is not possible for finding the Hamilton cycle. Now another graph number 3. In this Hamilton path is possible. E to A to B, B to C and C to D. But Hamilton cycle is possible? No. Here also no Hamilton cycle is possible, because for each and every vertex if a degree is greater than 2, then our Hamilton cycle is possible, or equal to 2 is also allowed. Now next is some property about the Hamilton cycle or Hamilton path. If a graph has a Hamilton cycle, then it will at least be connected. So for finding the Hamilton path or Hamilton cycle, compulsorily we have a graph as a connected graph. Second thing is every graph that contain a Hamilton cycle also contain a Hamilton path, but vice versa is not true. Third thing is there may exist more than one Hamilton path and more than one Hamilton cycle is possible in any graph. Now in Hamilton cycle, one important thing understand using this figure. If G is the graph in this figure, the edge AB, BC, CF, FE, ED, DG, GH and HI is considered as a Hamilton path for the graph G. But this graph containing the Hamilton cycle or not? Now check this thing. Now for this, consider the graph having a 9 vertices. If there is a Hamilton cycle in G, it must contain the 9 edges. So for covering all the nodes, we have to compulsorily require the 9 edges. Let us start at the vertex B and try to build a Hamilton cycle. Now here, if we start the process from B, then we have a two options, B to C or B to A. So here we can select the any option out of these two. So we select for example C. So we visit B to C for finding the Hamilton cycle. Now next is after C, we visit the node or possibility for the C to F or C to I. Both possibility are valid, but we select anyone. So for example here we select the node F. So visit the C to F node. So now after that we have an option for the F to E or F to I. But for visiting the node I, here when we check the two edges C to F and C to I, then we remove the one edge because we select the C to F only. So connected edges with the C is removed. So we can say that C to I edge is removed. So for visiting the I, we have to select the next edge as a F to I. So our path is like B to C, C to F, F to I. Now after I, we have only one option as a H, then H to G, like this. So in this way we cover the number of nodes. But here when we visit the G, then G after we visit the D, then after D we have a two option A and E. If we visit the node E, then no any path available from E to A or E to B is possible. That's why we can say that this graph is not considered as a Hamilton graph, because this graph not contain the Hamilton cycle, because Hamilton cycle is not possible. Now here from this graph or from this example, we carefully understand the some points. Few helpful hints from this problem is like this. First one is, if G has a Hamilton cycle, then for all V belongs to V, degree of V greater or equal to 2. So for each and every node having a degree greater or equal to 2, then this contain Hamilton cycle. Not compulsorily, but possibility for having a Hamilton cycle. But if you have a degree is less than 2, means degree is 1 or degree is 0, then never we will get the Hamilton cycle in this graph. Now second condition, if A belongs to V and degree of A equal to 2, then the two edges incident with vertex must appear in every Hamilton cycle for G. So if you have many Hamilton cycle possible in a graph, then you have degree of any node is 2, then in each and every option you will get this 2 node as your visited node in this graph. If A belongs to V and degree of A greater than 2, then as we try to build a Hamilton cycle, once we pass through vertex A, any unused edges incident with a vertex is deleted for further consideration. Because in, for example, when we visit B to C, then C to F we visit. That means connected edges with the C extra edges as a C to I. So we remove the edge C to I and we find the path as a next path. Now fourth one is, in building a Hamilton cycle for G, we cannot obtain a cycle for a subgraph of G unless it contains all the vertices of G. So this is a basic concept of the Hamilton cycle. Now following graph contain a Hamilton path or not? So check this thing. Now here first figure is a given figure. Now for checking the Hamilton path, we have a one concept is like, for give the some variable name to your graph. For each and every node, you have to give the variable name as a x and y. So basically, second figure is considered as a labeling of the your graph as a x and y. Now we start the labeling from node number A. So node number A as an inner node. Now node number A having a variable name as a x. So in place of A, we write the variable name x. First we label the vertex A with the letter x. Those vertices adjacent to a node A, namely B, C and D. So B, C and D connected with the node A. So give the variable name to B, C and D as another variable name as a y, because we give the name of the variable for A equal to x. So neighbor of the A not having the name as a x. So we can say that the name of the adjacent of A equal to y. So here label the y for the B, C and D. Now same way we repeat this thing. Means then they label the unlabeled vertices adjacent to B, C and D as a x, because we already give the y name in place of B. So adjacent of B consider the name as a x. So alternatively we give the label x and y to each and every node. So our resultant graph is like this. Now after that, this results in the label x on the vertices E, G and I. So x consider in place of E, G and I. Now after that we give this process or repeat this process for all the. So finally we label the unlabeled vertices adjacent to E, G or I with the label y. Means at this point all the vertex in G are labeled. So here see in the second figure all the nodes name as a x or y. Now after that, what is the concept in this example? Here after labeling x and y, here total number of node equal to 10, means mode b equal to 10. If G is to have a Hamilton path, then there must be considered as a 5x and 5y's. So see in this second figure, here no 5x and 5y is possible. So we can say that in this figure only x for x is available. So we can say that y equal to 6. So this is not possible. If Hamilton path is possible in figure, then exactly x and y count is same. So both the count equal to 5, 5. Then we can say that this graph is having a Hamilton path. So here no any Hamilton path is possible. So we can say that no any Hamilton cycle also not possible. So we can say that this given graph is not a Hamilton graph. Now after that, consider this some theorem related to Hamilton cycle or Hamilton path. So here first theorem is, let G equal to VE be a loop-free graph with mode V equal to n greater or equal to 2. So number of node is greater or equal to 2. If degree of x plus degree of y greater or equal to n minus 1 for all x, y belongs to V, x not equal to y, means your two node is not same, then G has a Hamilton path. So degree of x plus degree of y is greater or equal to n minus 1, then we can say that Hamilton path is possible in this graph. Now in this graph Hamilton path is possible like A, B, C, D, E. Now check the condition, degree of x plus degree of y greater or equal to n minus 1 satisfy or not. So mode V equal to n equal to 5, yes. Degree of A equal to 2. Now consider another node as a node y. So D consider as a node y. So here no any condition which node is considered. So you can consider any node as a degree of A equal to 2, then degree of D equal to 5. 3. Now next, degree of x plus degree of y greater or equal to n minus 1. Now for this condition, degree of x equal to degree of A equal to 2. Then degree of y means degree of D equal to 3. So 2 plus 3 greater or equal to 5 minus 1, because n equal to 5. So 5 greater or equal to 4, condition is satisfied. That means if the graph having Hamilton path, then this condition must be satisfied. Now next theorem related to Hamilton cycle is, let G equal to VE be a loop free graph with n greater or equal to 2 vertices if degree of V greater or equal to n minus 1 divided by 2 for all V belongs to V, then G has a Hamilton path. So here consider this graph. Here Hamilton path is possible, A, B, C, D, E. Now check the condition. Degree of V greater or equal to n minus 1 divided by 2 is satisfied or not. So mod V equal to n equal to 5, degree of A equal to 2, degree of D equal to 3. Now here check for the node A as your node V. So degree of A greater or equal to n minus 1 divided by 2. So degree of A equal to 2 greater or equal to 4 by 2. So 2 greater or equal to 2 condition is satisfied. Now next, for the node D also we check this condition, because here two types of degree is possible in this graph, 2 or 3. So D degree equal to 3. So 3 greater or equal to 4 by 2. So here we get 3 greater or equal to 2. So this condition is also satisfied. Now after that, another theorem about the Hamilton cycle is, let G equal to VE be a loop-free undirected graph with mod V equal to n greater or equal to 3 if degree of x plus degree of y greater or equal to n for all non-adjacent x, y belongs to V. Now here condition is degree of x plus degree of y greater or equal to n, but condition is x and y are non-adjacent node. Then G contain a Hamilton cycle. So here consider this graph containing the Hamilton cycle as a B, C, D, E and E. And Hamilton path is, many Hamilton path is possible. One is given here, Hamilton path. But here Hamilton cycle is also possible. Now for that, consider the mod V equal to n equal to 5, degree of B equal to 2 and degree of D equal to 3. Now here we cannot consider the node A and B because both are adjacent. So here we consider the first node as a node B and another node as a node D. So both are not adjacent node. So consider the degree of both is like this. Now degree of x plus degree of y greater or equal to 3. So degree of x and y addition is 2 plus 3 equal to 5 greater or equal to 5. So 5 greater or equal to 5 condition is satisfied. Means we can say that this theorem is satisfied for this example. Now another theorem is, if G equal to VE is a loop-free undirected graph with mod V equal to n greater or equal to 3 and if degree of V greater or equal to n by 2 for all V belongs to V, then G has a Hamilton cycle. So for this, consider the same figure. Now here Hamilton cycle is possible. Yes, A, B, C, E, D and A. This is a one Hamilton cycle. Also Hamilton path is also possible, because cycle is possible, then path is always possible. Now for this theorem, consider the mod V equal to n equal to 5, degree of B equal to 2, degree of D equal to 3. Now for this, here consider the degree of V is greater or equal to n by 2. So degree of B, for the node B we check this condition. So degree of B equal to 2 greater or equal to 5 by 2 means we can say as the 2. So 2 greater or equal to 2 condition is satisfied. Now after that, for the D also, degree of D greater or equal to 5 by 2. So here degree of D equal to 3. So 3 greater or equal to 2. This condition is also satisfied. That means we can say that this theorem is possible or satisfied for the Hamilton cycle. So here in this lecture we discuss about the how we can check Hamilton cycle or Hamilton path is possible in a graph. What is the Hamilton cycle? What is the Hamilton path? And how we can find the Hamilton cycle or Hamilton path in a graph. Thank you for watching this video.